It finally kind of settled for me what the point is that I'm trying to make there, which is that cognition is real. Right? It's not an epiphenomenon. It's not an epiphenomenon to say, oh, you have beliefs and desires and intentions, but really all the causal work is just these neurons firing. No, I reverse that. I say, no, those neurons firing have causal power in the system only by virtue of what they mean. If they meant something else, different things would happen. If you vary the details in such a way that they mean the same thing, you don't affect what happens.
Welcome to Brain Science, the podcast that explores how our brain makes us human. I'm your host, Dr. Ginger Campbell, and this is episode 213. Please visit brainsciencepodcast.com for complete show notes and episode transcripts. You can also send me feedback at brainsciencepodcast@gmail.com. Today, I will be talking with neuroscientist Kevin Mitchell about his new book, Free Agents, How Evolution Gave Us Free Will. I hope you've had a chance to listen to last month's encore episode with philosopher Thomas Metzinger, because he made several points that are very relevant to today's discussion. First, he emphasized that consciousness is a biological process generated by the interaction of the brain, body, and world. In fact, the body is so important that when the brain lacks access to information from the body, it replaces that information with experiences that include dreams and even out-of-body sensations. But if you've read much neuroscience, you're probably aware that many neuroscientists and philosophers have concluded that free will, which is our ability to make independent choices, is an illusion. There are many versions of this position, but to be honest, it has never really resonated for me, which is why I was drawn to Dr. Mitchell's counter-argument. Whatever your position on the controversy, I'm confident you will find today's conversation stimulating. After all, it gets to the heart of the theme of brain science. How does our brain make us human? And more importantly, why does this information matter to how we live our lives? Before we jump into the interview, I want to remind you that you can get show notes automatically every month if you sign up for the free Brain Science newsletter. Just text Brain Science, all one word, to 55444. There's also a link on the website. I also want to thank those of you who support the show financially. Brain Science is independently produced, so it relies on the support of listeners like you. I'll be back after the interview to review the key ideas, and I look forward to hearing your feedback. Okay, well, welcome back, Kevin Mitchell.
Thanks. Thanks very much. Yeah, sorry. Thanks for having me.
Kevin, could you start out just by telling us a little bit about your background and how it relates to how you came to write this book?
Sure, yeah. So I am a developmental neurobiologist, really. I'm a geneticist by original training and then did a PhD in neuroscience, but interested broadly in how the brain gets wired. So how does it get put together? What are the instructions in the genome that specify how the brains of different species get put together? And that question sort of brought me to the question of how that varies across individuals, especially in humans, with a kind of a convergence in science in the fields of developmental neurobiology or developmental genetics and behavioral genetics. It turns out really that people vary in their behaviors and personalities and so on, largely due to differences in how their brains develop. And the previous book that I wrote called Innate, which we discussed some time ago, is really about that. It's about how differences in the way our brains get wired shape who we are. And that question, I used to give talks about that, and people would often ask me, the premise of the book really is that we're not blank slates, that we do have psychological predispositions and propensities that we're born with or that develop from our biology, not anything that we chose. And people would often ask, well, what does that mean for free will? If I'm just wired a certain way and that affects my decision making, that's really what personality is patterns of decision making that are abstracted over contexts and over time, then am I really in charge, or am I just acting out my programming in some kind of a way? And that got me really interested in the question of free will from a philosophical point of view, but also the neuroscience of it, in the sense that the upshot of these differences in brain wiring really is differences in the parameters and the machinery of decision making. And we know a lot about that in neuroscience. And of course, the question of free will has been a topic of interest for philosophers for millennia. What was interesting to me was that those two areas didn't talk to each other a lot. If you look at the
Yeah.
philosophical literature, even though effectively what they're talking about is decision making, they don't, for the most part, engage a lot with the actual neuroscience of decision making that we're learning so much about. And then on the other side, the neuroscientists aren't always as conversant with some of the philosophical questions and issues as they might be, given that very smart people have been thinking about the ramifications and implications of these things for millennia. So really what I wanted to do in this new book, Free Agents, was to think about those things together, try and tackle free will and ask the question, does neuroscience, does behavioral genetics, does any of these other sciences really threaten or undermine our sort of common conception of being somewhat, at least, in control of our own actions?
Right. And there's so many neuroscientists who have come, and even some philosophers who are now saying we don't have free will, that it's all an illusion. And I haven't bought those arguments, but I hadn't really come up with this counter arguments. And so that's really why I was excited about this book, because I think you make a really good case and you come at it from what seems to me an original viewpoint. I mean, I haven't read every single book about this topic, but I want to say one thing about innate before we get back into free agents. Just the overall theme really was that your genes are not all that determines what your brain is, because development happens to each person uniquely. So if you were twins from the beginning, you're going to become different. But that doesn't mean that that's all there is. I think you used the word predisposition.
Yeah.
It influences how we act, but it's not the determinant of how we act. So the question is, how much control do we have over how we act? True,
yes.
right? And that's what we're going to talk about today.
Yeah, and I think that's really right. You've hit the nail on the head there for me. And I think what's really important, the language that we use here to describe these effects. So it's true that our genes influence our predispositions. But as you said, they don't determine them, right? That's not a deterministic relationship. And it's also true that our predispositions influence our behavior. But again, that's not a deterministic relationship. And so the point there is that there is some scope, some room in which some things can be genuinely up to us. And that's really what I tried to argue for. I guess people who've read the first book and who I hope they don't come away with a deterministic kind of picture, because I tried not to paint that, but they might still think, oh yeah, okay, we really are wired a certain way and that drives our behavior. And really this second book is kind of trying to say, no, that's not quite right. Our behavior is influenced, but not driven in that reductive way by our genes or indeed by our neurons.
Right. So who's the intended audience for this book?
Really, I hope it's a broadly educated audience. I've tried to write it in a way that's accessible. There is a lot of proper hardcore science in it, but I try to give really an overview of various areas as I understand them, and hopefully present the ideas in an accessible way, even if some of the details, maybe some readers won't get all of them, but I hope that the major sort of flow of ideas comes through.
So you give us an evolutionary account of how choice, value, and purpose, the things that a lot of neuroscientists are now telling us we don't have, but we're going to talk about the evidence that we do have these things.
Yeah.
And how we overcome this idea that we don't.
Yeah, exactly. Yeah. So it's interesting when you approach the question of free will, first of all, in the literature, usually it's very tied up with questions of moral responsibility. Right. That's why people in philosophy are interested in it, really, is the idea that if we don't, in fact, have some freedom of choice as individual agents, then our sort of presuppositions about moral responsibility go out the window. How can you blame somebody or praise them? How could you be justified in rewarding them or punishing them for something they've done if, in fact, they had no choice, and none of us ever has a choice? So that's usually the ground on which these debates are founded. And for me, that muddies the waters. Actually, there are implications for moral responsibility, but some of the literature I feel is kind of like motivated reasoning. In a sense, it's saying, okay, well, it's like accepting determinism, and we can talk about what that means in a minute if you like, but then saying we can still argue that there's some free will worth wanting, for example, to choose Daniel Dennett's term.
Yeah.
Yeah. And so Dan Dennett ends up with this view that's known as compatibilism, where he sort of makes this argument for free will that is sufficient to protect our notions of moral responsibility. But I wanted to ask a different question and leave the moral responsibility implications towards the end, because I think our systems of morality are all tied up in all kinds of other issues of just pragmatics and legal systems and the evolution of pro-sociality and all sorts of things like that. And then the other thing that characterizes most of the discussions about free will is that they're totally human-centric, right? Everything about the discussion is centered on human beings. And then that gets tied up with questions of things like consciousness. And I think there's a deeper kind of question, which is not how can humans be in control of what they do, but how can any organism be said to do anything? How can it be acting in the world as opposed to stuff just happening? Right? And for me, that question of agency really is a very central biological question. I think that's a central property of living things, is that they can do things, unlike, say, a rock or a planet or an electron. They don't do things. Things just happen to them or near them or in them, but they don't act. And so the tack that I've taken in the book is to, rather than starting with the most complex instantiation of this phenomenon that we're interested in, which would be human beings, I wanted to start with the simplest one to try and ground the concepts that I think we need in order to get a naturalized account of free will in humans that doesn't invoke any kind of magic or mysticism. And that's why I paint this evolutionary picture, really following a trajectory from the origin of life itself, because to me, in this discussion, it's important to understand what being a living being entails.
Right. So that's one of the notes I have here, is that you use the phrase in the book several times. The story of agency is the story of life itself. And that's basically what you just said.
It is. And it's funny because I don't think that's a widespread view in biology. And if you open a biology textbook, and they usually start with the characteristics of living things, and it might have replication and metabolism and respiration and a few other things like that, and they are characteristics of living things. But to me, it sort of misses out the bigger picture. Like, why do they have respiration and metabolism and replication? What's the point, right? What's the point of being a living thing? And what really is the essential difference between life and non-life? And for me, that central difference is activity. It's that living things are hives of, in this usually chemical activity, right? And they're trying to keep themselves alive. That's what being a living thing entails, is that you've got this sort of collection of interlocking processes. And they're not just doing metabolism, for example. Each of them is also contributing in a way that constitutes all of the constraints that keep the living system organized in the way that it is. So it's a sort of a closed system of control or constraint that is aimed at persistence. That's its goal. And that's a real thing, right? It's not a mystical sort of sounding thing to say that it has a goal, because it's a very definable, naturalizable kind of thing. I mean, evolution doesn't have a goal, but evolution led to the emergence of living things which do have a goal, which is to persist. And that kind of grounds everything else that they do, in the sense that natural selection ensures that all of the interrelations of all their components and all the functionalities of different subsystems and so on are aimed at persistence, simply because if they weren't, that thing wouldn't be here.
Right. And I really enjoyed, first of all, I want to say that your approach reminds me of some of the early embodied cognition writings, because the point at which living things exist and essentially make choices is when they become separate from the rest of the world. So that leads us to the cell membrane, right? Why is that such a critical step?
Well, the invention of the cell membrane, and we don't know how it happened exactly, but maybe in, around hydrothermal vents or something, there were these little rocky crevices where, thanks to a supply of free energy and the right kinds of chemicals, these sort of interlocking sets of chemical reactions could arise and evolve and get more complicated. At some point, they got complicated enough to generate these lipids, which would make a cell membrane. And when that happened, what it really generates is an entity that is causally insulated from the rest of the world. So living things are trying, right? They're having to do thermodynamic work, energetic work to keep themselves organized, because otherwise the second law of thermodynamics says they should just become disordered. So they're having to do that, and they need to take in free energy and they need to take in raw materials, but they also are out of equilibrium with their environment. They're not just in total equilibrium. And so the cell membrane is that key barrier that enables the thing to be a thing, right? It makes it an entity. It has an inside and an outside. And what happens inside is causally insulated from what happens outside. And that's a really key transition, I think, that makes living things different from non-living things.
I will just tell my listeners that I think a lot of them may have already read about the theory that life started at the deep vents, but I hadn't. So that was new to me, and I thought it was a fascinating account. And I'm going to encourage my listeners, when they read your book, to for sure read that, because it's a great starting point. I had never thought about the fact that all biochemistry is essentially driven by hydrogen ions. I mean, that just blows me away.
It does. And you know what? It is a great story. And the one I present is sort of the story that I find most convincing. And it comes from people like Bill Martin and Nick Lane and many others. And yeah, you've hit the nail on the head, right? You need this supply of free energy. And in this case, it's hydrogen ions. And that may have come really from the Earth itself to begin with. But actually, all living cells still use that mechanism, and they generate a hydrogen gradient, proton gradient basically, and they use that to power a protein, which is like a little hydroelectric dam sort of thing, right? And so yeah, all cells use that mechanism. They generate internal stores of energy using that mechanism, and you can see in that this sort of constant striving, right? I mean, this constant process, this flux. A living thing is just a collection of processes organized in a certain way, but they're all in flux all the time. And that dynamism is really the key aspect of life. And when that stops, right, when the activity stops, then the thing is dead. And
Right.
so,
All the stuff's still there.
yeah, all
So
the
it's
stuff
not
is still
about this.
there.
It's not the stuff. It's the process.
Exactly. And what that means is that it's right, in my mind, to think that a system that's set up like that thereby has purpose or a goal, which is to keep all that activity going, right? And the really crucial thing about that is that that purpose then grounds meaning and value. Because once you're a cell like that with a membrane, you've got an inside and an outside, you're trying to keep yourself going. Well, it pays to know what's going on outside. You want to be causally insulated, right? You don't want to be pushed around by every physical or chemical force out there. But if there's stuff going on out there that you need to know about, like food is running out or oxygen's running out or something like that, it's good to know that so that the cell can reconfigure itself. And then what that means is that now the cell, the early life forms developed sensors and receptors for chemicals and for other sorts of conditions like, pH or temperature or things like that in their environment that they could then respond to in two ways. So they could take that information and they might reconfigure their metabolism, say if one food source is running out and another one is available. Or if oxygen is running out, they can switch to anaerobic respiration, that kind of thing. And that's a really good trick, right? Obviously, that'll help an organism persist in a dynamic and unpredictable environment. Another good trick, though, was the invention of behavior, where the organism could move. And so one solution to there not being enough food around is to move and look for food somewhere else. And so that really set up this dynamic where signals coming from the outside have some information, right? You've got a receptor, it binds, say, a sugar molecule on the outside of a bacterium, for example, and it gives a little wiggle inside, right? It's a protein that spans the membrane. It binds something on the outside. It gives a little wiggle inside. And there's no sort of physical energy that's been transmitted. Nothing's being pushed around. It's just information. It's just a conformational change. But it tells the cell that it should move this way or that way, for example. And that's how bacteria move towards a food source. And so what you've got now in that situation is what I consider to be a perfectly naturalized condition of meaning, right? You've got meaningful information. That is a signal that's about something out in the world that just correlates with it physically. And that information has value to the organism. It's either good or bad in terms of to have a certain response to it. And it's good or bad relative to this purpose of persisting. So those three things, meaning, value, and purpose, to me are perfectly naturalizable, but they're in a lot of sort of philosophical stuff. And I think a lot of scientific thought, people find them a bit nebulous, a bit slippery. The idea of purpose in particular was kind of banished from polite scientific discourse with the fear that people were slipping into a kind of a cosmic teleology where they were thinking, okay, well, it's the whole universe has a purpose, or evolution itself has a purpose,
Right.
which I don't think is right. I don't agree with that view, but I do think it's right that evolution imbues living organisms with a purpose.
So scientists have discovered that even these single-celled organisms have complex systems, and they can integrate multiple signals. And you argue that they're able to act as agents, make choices. But how do you justify calling them agents rather than just viewing them as complex machines?
Yeah, so this is the key question, and you can extend that question all the way up to humans, right? So some people would say, they look at a simple bacterium and they'll say, well, look, it's just this protein binds that thing. It's a chemical interaction and it sends a little wiggle, the conformation changes, this other protein binds it, it phosphorylates that one, it causes the flagellum, which is this outboard motor of the bacterium, to rotate this way versus that way, and it changes direction. And you can draw a kind of a very clear mechanistic linear pathway of control, like it's a control system that you could build in a robot. And none of that, the danger is then you look at that and think, well, the bacterium's not doing that, right? It's being pushed around by its parts. That's what's happening. What's happening inside it is determining where it goes. It's not the bacterium as a whole that's doing that. And you can, in fact, do experiments in the lab that isolate and control everything else and just look at that one linear pathway, and you'd be left with that impression. However, that's not how bacteria or any other organism actually encounters the world, right? Nature is not so accommodating as to present just individual sort of stimuli or environmental factors one at a time in isolation. Instead, the problem really facing a bacterium or any other living organism is this constantly changing environment, loads of different factors varying all the time. And the organism has to first, at the most basic level, be able to react to things like that, but not in a simple way, because you may have, for example, where there's a food source, there may also be a threat. Maybe the temperature's too high for the bacterium, and then it doesn't want to go there, right? So it has to integrate multiple signals, multiple chemical signals in the context of things like temperature and osmolarity and pH and crowding and its own recent past history and so on. So really what's happening is it's making an integrative decision at the whole cell level based on these configurations that all in effect embody reasons, right? It has a reason to go towards food. It has a reason not to go towards high temperature and so on. They're all kind of configured by natural selection. So the upshot then is to say, well, you can get one of two views of that. Either it's a really, really complicated machine in which all these things are happening, or it's an agent, or at least a proto-agent, a basal kind of agent that is a proactive animal, right? I mean, it's a proactive organism. It's not just sitting there waiting for information to be pushed around by it, right? It's proactive. It's keeping itself organized. It's moving around in the environment, and it's integrating all these signals for reasons that are not the reasons of its parts. They're the reasons of the whole organism.
Right.
And that, I think, is really key. And so I do argue, and I have with my student Henry Potter in a paper that we've written on the subject, argued that even the most primitive organisms that we know of, like single cell bacteria, can be thought of as having at least a minimal kind of agency, and that the story in evolution is one of elaboration of that agency, so that the organisms that evolved got more and more causal autonomy from the exigencies of the environment, and were better able not just to react to things in the world, but to predict and anticipate and then plan ultimately over longer timeframes.
I appreciated the distinction you made in the book about the difference between asking how and asking why.
Yeah. Yeah, it's a tricky one because, again, why questions are sort of frowned on in science often, and even in biology, which is odd because, well, I mean, the answer to most why questions in biology, why is it the way it is? The shortcut answer is because it's adaptive, right? That's usually the answer. It's not always, but often, right? But in fact, I mean, that's not a throwaway answer. That's the key answer, right? I mean, that's what life is about, right? If you don't take an evolutionary historical view of it, you're missing the whole point. Life is a historical evolutionary process. And the why questions then are key to that. And really, in a sense, you can just think of them as how questions that are extended over much, much longer periods of time, as in, how did it come to be this way? And the answer to that usually involves and hinges on these questions of purpose and meaning and value, right? You can ground the why questions ultimately in what is it that favors the persistence of the organism. And that also, I think, gets us away from this sort of instantaneous mechanistic view of what organisms are doing. Because if we take our bacterium again, for example, you can look in a moment and say, okay, what's happening is this thing is being triggered and it phosphorylates that one in the chain that I said earlier, right? And that's our explanation. This is how this signal leads to this change in movement. And you might think, well, then we're done, right? That's
Yeah, that makes the cell a thermostat.
Exactly. And it erases all history, right?
Right.
It erases all traces of history from your explanation. Instead, you can also ask, okay, but why is it set up? Why is it configured in such a way that when this thing binds, this protein binds, and this is the effect? And there, the only answer that you'll eventually get to is it's configured that way because it's a good thing for the organism to move towards a food source. That's a real scientific explanation. It's not a hand wavy mystical kind of a thing. And if you're not considering that, if you're just thinking of biological things as machines in the moment, then I think you're missing out on the whole thing that we're really trying to explain, which is how life persists through time.
Right. So the bacteria, just taking them because they're the first piece of the chain, not simple, they are not just little algorithms like a thermostat,
Yeah,
because they're not just passively sitting there waiting for something to trigger their behavior. They're
exactly.
proactive. They move
Exactly.
around. And what they do in relationship to their environment depends on their history and the current context. Are they hungry? What else is around?
Exactly right. So they modify their reactions to things depending on those factors that you just mentioned, right? Current history, current internal state, what's their metabolic state right at the moment. And of course, all organisms have to do that.
Yeah, I really want to emphasize that point because one of the arguments against free will is just the idea that this is all just, a mechanistic reflex thing.
Yeah,
And as you point out in your book, one of the key, and I've had other guests that pointed out the same thing, key point being that you don't get the same result every time to the same stimuli. So it's not a reflex.
yeah,
That's a pretty simple explanation of the difference between a reflex and a choice. I can't
yeah.
choose whether my knee jerks when if someone's tapping me with one of those hammer things.
Hmm.
I don't choose that. That just happens.
Yeah, but so the key thing is, yes, that these, when you get to more complicated scenarios, and even in simple organisms, the response to any kind of a stimulus may vary over presentations of it because the organism is in a different state, for example. So in a sense, when it's in state A, it has different reasons for
Right.
behaving than when it's in state B. On top of that, there's also just some indeterminacy at play. in that these things are made out of messy, jiggly, jittery, small components that jitter around. They're subject to thermal fluctuations. The precise numbers of protein molecules vary in a cell kind of probabilistically over time. So they're not algorithmic, right? And they're not tightly specified deterministic machines. There's some wiggle room at play there. And sometimes what happens is just the outcome of a wiggle, right? Some random thing. But the broader point is that actually that wiggle room gives some space for the organism as a whole to have causal power in what happens in the whole system. So it gives a kind of an opening for top-down causation because there's some indeterminacy at the lower levels.
Yeah, and I'm going to get into that with you in a few minutes in more
Yeah.
detail. So the first half of your book, you make a convincing argument that the evolution of life is the evolution of agency, purpose, and meaning, because even the simplest organisms make choices in an effort to survive. But some listeners might be wondering, well, what about all those scientists and philosophers who claim that choice and free will are illusions?
Yeah. So, yeah, I mean, I try to tackle these a little later on. And the reason I take this approach is, I mean, I start the book by laying out what I take to be some of the challenges to the idea of free will. And I'll say what those are in a minute, but they're challenges in principle, right? There are arguments that say, for these reasons, we could never have free will. Right? There's just no way that actually anything that could make a choice just doesn't exist. So there are arguments against free will in principle. But what I wanted to do was actually start with the story of the evolution of agency as I see it in practice. And just say, well, okay, we're going to shelve those. We're going to get to them, to those big issues, but let's just look at what happened. And let's just start with the actual science of what we know about how things make decisions and control their actions and control their behavior. And then, so once I've done that, I come back to these big questions and I'll lay them out. Let me go in reverse order, starting with at a high level, which is where we started the conversation, actually, kind of an idea of biological fatalism. The idea, okay, I'm sure I can make choices, but my choices are driven by the way my brain is wired right now. And that's a consequence of my genes and the way my brain developed and maybe my experiences, but things that I didn't necessarily control. So I don't have free will at all. I'm just acting out my programming. That's one level. You can go a level deeper, which I think a lot of neuroscientists find a bit seductive, where we're learning more and more all the time about the neural circuits of decision making and behavioral control and action selection and motivation and goal selection and all kinds of things, right? We can look in humans at these activities as they happen. We can look in animals, and we can even manipulate them in animals. We can, go in, change the activity of very specific circuits, make an animal more sensitive to rewards or risks, or more confident in its decision making, or more willing to wait for a reward over a longer time. All these different parameters that affect the decisions it makes. And once you start doing that, it's kind of hard to get away from the idea that in revealing all these mechanisms of decision making, we are revealing just mechanism. That we're just showing it just is just mechanism. There's nothing else, right? It doesn't matter. There's no real sort of mapping to cognitive or psychological states like beliefs or desires or intentions. It's just this neural circuit fires, then this one does, then that one does, and it's a big, complicated neurochemical machine. So that's a view where you're reducing the concepts of cognition and psychology to just neuroscience explanations, where you're saying the reason the animal did such and such is because this circuit fired, then that one, and this one, and so on. So that's a kind of a neural reductionism. And it's, like I said, it's sort of seductive because we get these really great looking explanations at that level within neuroscience these days. And then, but it's funny because I think, some physicists might look at that and just kind of scoff and go, look, guys, come on. You want to look for the real explanation. Well, all those neurons are just made of atoms and molecules. Your brain is just atoms and molecules that are physical stuff, same as all the other physical stuff in the universe. They have to obey the laws of physics, which are deterministic. And so what the atoms are going to do, they're just going to do whatever, right? Based on the laws of physics. They're pushed around by gravity and electromagnetism and strong and weak nuclear forces. And that's where the real causal power lies. And anything else is just kind of a cute way of talking, right? It may be a convenient way of thinking that you have a complicated system. We'll talk about neurons instead of atoms, but really all the causal work is done at the lowest level, even if it's very complicated.
Right. And that's why you had to get into the whole issue about determinism and what quantum theory really says.
Yeah, exactly. Because if you start there with that question of physical predeterminism, the idea that everything that happens, if, for example, you knew the complete state of the universe right now, all the positions and momenta of every particle in the universe, and you plug them into the Schrödinger equation or some other equations that describe how quantum systems evolve, the state at time t+1 would be determined by what we know now and the laws of physics. And there would only be one possible future, and that would go to time t+2 and t+3 and t plus the end of infinity, basically. And once you start thinking like that, and it's an old idea. I mean, Laplace had this famous idea of a demon that could see all of this thing and then would be able to, I mean, what he said was the entire timeline of the universe would be laid out in front of this demon all at once, right? There's no difference between the future and the past in that scenario, because the implication is that everything I'm saying to you right now and you hearing me say these words was determined at the point of the Big Bang. Right, which just seems kind of silly and like it couldn't possibly be true, and yet there's a whole edifice of physics kind of built on that scenario. However, there's also lots of physics that says, well, that's not the case. That actually there's lots of indeterminacy at the lowest levels, and indeed even at what are called classical levels. And so what I try to do in the chapter that looks at the physics, it was wrap my head around what the implications of quantum physics really are. And now I'm not a physicist, so I struggle to get to grips with that. But the upshot, based on my sort of best understanding of physics, talking to lots of physicists, is that there's lots of indeterminacy clearly at the quantum level. I mean, we know that from the Heisenberg uncertainty principle, which says you can't know both the position and momentum of a particle with infinite precision at the same time. And people look at that and they've interpreted it different ways. The way I just worded it, you could think, well, that's a statement about what we can know.
Mm-hmm.
It's not a statement about the particle or the nature of the universe. But in fact, it is mathematically a statement about the particle. It's not about what we know. The particle does not have infinitely precise position and momentum at the same time. It can't do. And so if you think about the way quantum systems evolve, and basically everything is a quantum system, really, they evolve according to the Schrödinger equation, which is really deterministic, but what it determines is a map of probabilities.
And that's the tricky part, right?
That's the tricky part. And people have different interpretations of that and where this probabilistic nature comes from. But the point is that whenever you want to define the way a system actually behaves in over one single run, these probabilistic events just sort of play out. And you're left with the one potential outcome from this web of probabilities that was there. And it doesn't seem like there's anything else that's causal there. It seems like real randomness and indeterminacy.
Right. And you mentioned in the book Carlo Rovelli's work, and I actually love the fact that you talked about his book Heglerland, because I wasn't aware of it. And so I've actually read it twice, because it's a wonderful book. And I actually tried to get him to come on the show as a follow-up to you, but unfortunately he's too busy. But, he makes I think a good physics explanation of this indeterminacy. He has a particular interpretation, which is called the relational interpretation of quantum theory. It's actually the first one I've ever read that I went, yeah, that really does make sense. Yeah. It might be a fringe theory, but to me, it makes sense, and it fits in so much with what we know about how living things behave, for sure.
Yeah, absolutely. I agree. And I like the relational view very much, both in terms of physics, generally quantum physics, but also for everything. The idea that the properties of any object are not intrinsic to it. They all inhere in the relations that it has to other things. That's what a property is. There aren't any private properties that don't have an effect in the world. Otherwise, we would never know about them, right? The properties that we know of are always relational with something else. And I think that I don't want to jump ahead too much, but I think that grounds also our biographical self, actually, through time. That's very much a relationally defined thing. But just to get back to the physics, I also have had the same feeling that a lot of the arguments people have put forward in the physics field, for example, about the quantum to classical transition, the idea that quantum stuff is indeterministic, that's fine. But when systems get big enough and complicated enough, when they have enough interacting components, that probabilistic nature somehow washes out and things become completely deterministic.
Mm-hmm.
And so if you're in Newton's world, you can predict the orbits of the planets and solar eclipses and things hundreds or thousands of years in advance, right? Really, really precisely. There's no apparent randomness at play. But in fact, there's good reasons to think there's still some indefiniteness at play in what we define as the future. Actually, though the future, things are not fully defined in the future. And there's some interesting work by Nicolas Gizan and Flavio Del Santo and others about, this gets really deep and I never expected to go down this rabbit hole, but it's really about the philosophy of numbers, of real numbers. What is a number and how are they given in the universe? Are they just given with infinite precision all at once? Because that's actually the assumption on which the idea that classical mechanics is fully deterministic rests. And if they're not given with infinite precision all at once, then there's some room for some wiggle, some indefiniteness and some indeterminacy, even in classical systems. And so anyway, ultimately, I don't want to dwell too much on the physics, but ultimately, the point of that chapter is that the future is not written. The future really is open. It's not necessarily a world of sort of branching possibilities that are already laid out in a definite way that then are simply chosen between. It's more like a fuzzy, indefinite world where things are not fully defined and they become defined through interaction in the time period that we experience as the present. When events are happening, that's what events are, is things interacting, and where those parameters that describe them physically are becoming defined because they're catching each other in interaction, and then they become fixed and they move into the past. So yeah, I think there's sort of interesting ideas in there about the nature of time and the nature of probability and indeterminacy that get down multiple sort of philosophical rabbit holes. But the upshot is that systems are not fully determined by the low-level physics.
Right.
Now, if that's true, then the usual rejoinder that people will pose, if they're skeptical of free will, is to say, well, look, that's no better. That's no better than the system being fully determined by the laws of physics, in which case I have no free will. You're just telling me there's some randomness at play. I'm still not in charge of that. So how does that give me free will? It doesn't by itself. And they're right. It doesn't by itself. It's a prerequisite, I think. It's a criterion that has to be fulfilled for free will to even, or agency of any kind, to get off the ground as a concept or as an evolutionary reality. And the answer, I think, is that level of underdetermination by bottom-up causes allows for top-down organization to have some causal influence over how the system evolves.
Right. And there's just so many great ideas in your book that we don't have time to talk about. But the bottom line here is that there's not anything in the laws of physics that prevent the existence of agency or free will, because the universe is not deterministic. If it was, then the argument that free will can't exist would be over. But what does this indeterminacy really mean at the level of the neurons?
Well, it's a great question, and it's an open one. I think there's some controversy about
Right.
whether neurons are really noisy or not. So I mentioned earlier that in bacteria, they're made of, their components are proteins that are moving around and chemicals moving around in the cell. They're diffusing at random, they're bouncing into each other, and so on. So they're wet and jiggly, jittery kind of stuff. And it's not surprising that there would be some outcomes of that inherent sort of randomness in their components or noisiness of their components that could manifest at the level of the whole cell. And that's true in neurons as well. And so in many cases, neurons, when they fire an action potential, you've got ions flooding in, they go down to the synaptic terminals, and if they release enough calcium at that point, then synaptic vesicles will fuse with the membrane and they'll release neurotransmitter. And then on the receiving side, the neurotransmitter, if it's bound by receptors of the receiving neuron, will cause ions to flow into that cell. And if enough of them do that, then it causes this amplifying process, the action potential, and then that neuron will fire a spike, right? But those things don't happen completely reliably all the time, right? There's lots of times a neuron fires a spike and synaptic transmitter is not released, or enough of it is not released to trigger spikes on the other side. And even at the really small levels, sometimes ion channels just open by themselves. That's a probabilistic conformational change that just has an equilibrium point, but it's basically probabilistic. The same is true for synaptic vesicles fusing. So at a molecular level, neurons are noisy. They're noisy components. And it was interesting, even John von Neumann, who was thinking about the computer and the brain, recognized this challenge. How do you build a system capable of cognition and computation when it's made from these actually really unreliable individual components? And of course, the organisms go to great lengths to build brains that are reliable, that can do cognition with these jittery components. And they do that by building multiple things in parallel and putting more proteins in and all that kind of stuff. But there's still some noisiness, right? And if we record from the brain, for most neurons at least, if you give a little electrical pulse or some kind of a stimulus to an animal or something like that, you'll get different kinds of readouts over time. Not always, and this is where some of the controversy in the fields comes in, because some neuroscientists would argue strongly that that noise, the apparent noisiness or variability, is not due to molecular noise. It's just due to some ignorance on our part of other things that are going on in the brain that are affecting that particular neuron that we're recording from, for example. And that may be true in some circumstances. But ultimately, what it means is that the brain is not a deterministic machine, just driving electrical impulses or just flowing through it like they flow through the circuits of a computer.
Right.
That's really not a good metaphor for the brain. It's far too mechanistic and deterministic, when in fact there's a lot more flux and sort of variability in the precise low-level details at any moment. And that has important implications.
Right, because there's been many scientists that I've talked to over the last few years talking about the importance of the spontaneous activity of the brain.
Yeah.
And that's part of that. Would you take us through the overview of how this could support choice, the noisiness?
Sure. Yeah. Well, again, it's kind of an extension of the idea that the causes are not all bottom up. Right? And so we sort of dispense with the view that they're all bottom up from the level of physics, but maybe they're really bottom up from the level of neural circuits. So what the neural circuits are doing determines what happens. And the implication there is that it doesn't matter what the firing of those neural circuits means to the organism. If they fire, then whatever's going to happen is going to happen. Right? So it suggests that things like beliefs or desires or intentions or other cognitive states are mere epiphenomena. They come along for the ride, but they don't in themselves have causal power. And so one of the key sort of arguments that I make in the book is to actually look at how neural systems work. And what you have to realize is that actually the low-level details get either averaged out or filtered out or coarse-grained over all the time.
Right.
They're
Vision's
lost.
Vision's the perfect example.
Absolutely. They're lost from moment to moment. And in fact, in our visual system, right, we're not perceiving all of the photons that are hitting our retina in some kind of massive matrix-like array, right? What we perceive is the outcome of a bunch of computations that are doing, for example, contrast enhancement. They're comparing the photons hitting photoreceptors that are next to each other or near each other to try and figure out where there are edges, where the illumination intensity or frequency has changed. Right? And so the information that ultimately comes to our visual cortex is already massively processed, and it's coarse-grained, and loads of the low-level details are lost. And what's left is the meaningful information that the organism cares about. Where are the edges of things? Where are there objects? What types of objects are there? Where are they moving relative to me? That's information that the organism can act on. So that kind of thing happens all the time, and it happens even from one neuron to the next. You have these sort of cartoons we see all the time of neuron A, and it fires, and it releases neurotransmitter onto the dendrites of neuron B, and then neuron B fires. And in fact, what usually happens is that neuron B is doing some integration, right? So when neuron A fires, it may have to fire 5 or 6 action potentials within a certain time period to be sufficient to activate neuron B, right? It's integrating its inputs over some time window. And of course, inputs from multiple neurons usually. But what that means is that it doesn't care about the precise timing of every spike in neuron A. That information is lost. What it does is integrate over that and ask, what's the rate? Is the rate above a certain level? Then I'm going to fire. Is the rate below a certain level? Then I'm going to ignore it. So rather than having a kind of a driving scenario, I like to reverse that perspective and think about neuron B as the one in charge. Neuron B is monitoring its inputs. And like a single-celled organism, it's saying, what's the state of my environment here? And then what should I do? Right? It's sort of like an individual decision-making unit. And I think if you reverse that perspective, you move away from this passive, reactive driving kind of a thing to much more of a proactive monitoring, local decision-making sort of apparatus where the low-level details don't really matter. What matters is the pattern. And the pattern means something to the organism. And that's even more obvious when you get to high-level populations of neurons, because in our brains, with so many millions, billions of neurons, really it's patterns of populations that carry the important information. And there, again, you have one population of neuron that's monitoring another one. And if this population A, is in a state that signals something, like there's neurons in my brain right now, populations of neurons that are signaling that there's faces out in the environment and that one of them is your face. Right? So that's the meaning of those patterns of activity. However, the precise details of those patterns can vary, and they won't have any effect on this other population that's monitoring them because it doesn't care about the details. It cares about the meaning. If suddenly your face changed into the face of Brad Pitt, then there would be a different macro state pattern that meant something different. So really, it's ultimately this the low-level details not mattering that much, not being the causal difference makers in most cases, means that it's the higher level meaning of the patterns that actually has causal power in the systems. And that's because, like in our bacterium, we have to ask the why question. It's the higher level meaning of the patterns that actually has causal power in the systems. And that's because, like in our bacterium, we have to ask the why question. How did it get structured in that way? What is the configuration that sets the criteria for action or for thought or for internal reasoning and so on? So, yeah, so that's the gist of that argument. And to get there, I do go through a lot of the neuroscientific details of how decision making actually works, how action selection works, starting with sort of simpler organisms like nematodes and hydra and stuff like that have very quite simple action repertoires to choose from. Move forward, move backwards, bend this way. They only have a few things they can do, but they have systems that are set in place to decide between them for the reasons of the animal. And those get elaborated over evolution to the point that we experience ourselves as us doing things for reasons where, again, it's the meaning of those patterns that is the important thing.
So we're running out of time, but I want to ask you to talk about the two-stage model of free will, because it kind of puts a lot of these pieces all together.
Yeah, it's really, really interesting. So that two-stage model of free will was first proposed by William James in the late 1800s. And basically, he argued that while at any moment when we encounter some scenario, some things occur to us that we could do, right? So as we're talking here, some things are occurring to me of things that I could say. Now, I'm not really necessarily actively involved consciously in those ideas popping into my head. However, once they do pop into my head, then I'm involved in selecting among them. So the idea of the two-stage model is that in any scenario, an organism, certain ideas occur to it. And if it's a very familiar scenario, there may be a very habitual kind of response to it. And so when someone says good morning to you, you may just habitually say good morning back or hello or something like that, right? You've got a small range of options. But if you're in an unfamiliar scenario, maybe you don't really know what's the best thing to do, and some ideas occur to you, and you may just do one of those, see how it turns out, right? Or you may kind of consider them and simulate in your mind what would turn out to be the case if you did that, and then make a decision on that basis, right? And that's how most of our action selection happens, is we sort of anticipate the future outcome. We evaluate the utility of that outcome if we did action A versus B versus C, and then we pick the one with the highest utility. So the two-stage model has some randomness in it at that first stage.
Mm-hmm.
So not completely random, right? Not arbitrary suggestion of things that you could do, but not entirely constrained or determined either. And the really, really interesting thing is that there are systems in place in multiple organisms, including mammals, including humans, that can actually kind of calibrate the degree of randomness there. So you might find, for example, you're in a new scenario, you try something, it's not working, or you've been trying to achieve some goal and you just can't, and you're getting frustrated. And what you want to do is go back to the drawing board and think of some new things to do, but outside the range that you've explored so far, right? So you want to think outside the box in a more creative, problem-solving kind of way, right? And there are systems in the brain that will raise the temperature of that search mechanism and suggest some wider kind of range of options for you under those scenarios. So we can, in a sense, choose to modulate the randomness of some of those neural processes in a way that then gives us some raw material to choose from in our more, in the selection of actions and the actual execution of actions.
Yeah, I thought that was really cool. I found myself thinking about, when it's not, this is a very simple example of, you're going to go out to eat, right? And you say, oh, what am I in the mood to eat? Right. And so some possibilities pop into your head and you go, no, not that one, not that one. And then you pick the one that feels like a good choice in that moment. And that's the example I thought of when I read this. One of the key points here, and continues through your book, is the important idea that the present is not instantaneous, that it has duration. And I don't think that's going to be an idea that people have necessarily heard before, because that's really where the choice has to come in, is in the indefinite present, right?
Exactly. I think that's a really key one. And, it comes from, well, it's an old idea, but Henri Bergson was one of the sort of major proponents of it. But the idea being that we should think of time as having, periods of duration, not instants that have zero duration. Because, of course, if you add up a load of zero duration time points, you don't get anything, right? So that's just an idealization, that sort of thing, but it's not real. And in fact, we experience the present as having some duration. It's not just an instant of zero duration. And as I said earlier, one way to think of that is as the time during which the indefinite becomes definite. Right? And for physics, that may be just things interacting. For us, it may be that resolution of choice, the action of decision making in the present that is really us exercising our own agency in that time period to settle how things go. And I think that is kind of provides for me an answer to this thought experiment, which is to ask, well, if you rewound the tape and put the person in exactly the same scenario that they were in at time t, with all exactly the same state physically of their brain, could they have done otherwise? And people like Dan Dennett, who argues for free will, but on a compatibilist line, would say, well, no, they couldn't have done otherwise. I mean, they might have done otherwise if circumstances were slightly different. For if they had a different reason for doing something, they might have done otherwise. But if you put them in exactly the same state at this time, they couldn't have done otherwise. And for me, I have to ask, well, wait a minute, what time is that you're talking about? That's not an instant, right? And it's not a time that just has a static state that can be fully defined in the way that the thought experiment sets up. It's a duration over which things are in flux, and in that period, there's opportunity for the organism as a whole to settle how that flux plays out. So that's the argument. And yeah, I think it is a key point, and it probably isn't one that many people will have thought of before. I certainly hadn't really dwelt on it at all before I got into researching some of those other writings of people like Bergson.
Yeah, I have to apologize because I think we've got only through about half of the things I wanted to ask you.
Oh, that's
So
okay. I've
I'm
been too
gonna
long-winded.
so I want to just ask you, what else do you want to share before we close? Since I mean, it's a big, big topic, and I
Yeah,
really am
it
going
is.
to recommend to my listeners that they actually read your book. Hopefully, this just is almost a teaser.
Yeah,
You
yeah,
probably listeners may have a lot of other things they've heard that they're wondering that we don't have time
yeah.
to get
Well,
into. So
there's one
what do you
final
think?
thing.
Yeah, what's the most
There's one
important?
final thing. So there's one final argument that many people make about free will, where they can say, okay, you've made a convincing case that organisms can do things for reasons, including us. However, so you can say we can do what we want, but can we choose what we want? Can
Mhm.
we want what we want? I mean, that's an old argument from Arthur Schopenhauer amongst others. Sam Harris also makes the same argument.
Right.
Robert Sapolsky makes the same argument as well. And so, what they will say is that, these reasons, as I just described, kind of bubble up to our consciousness. We have no window on them. They're completely opaque as to why those occurred to us. We have no insight. We have no way to intervene in those kinds of processes or change our reasoning or want different things. And to me, that's just wrong. I just don't see. I mean, it seems obvious to me that, in fact, we do think about our thoughts all the time, and we do reason about our reasons all the time, and we talk to each other about them. We actually have quite good introspection, even though there are scenarios in neurological patients, for example, or some kind of psychological experiment setups where people can be fooled into doing things for reasons that weren't really their own. To me, those kinds of exceptions are like optical illusions, right? They kind of illuminate that there is a system
Mhm.
that can be fooled, right? They don't show that the system never works right. Optical illusions don't show that we never see anything that's actually out in the world. They show how we see things in the world. So my view of that evidence is it shows how we do introspection. Yeah, it's fallible, but we do it. And so we have in humans this final stage of evolution along our lineage is the evolution of metacognition, where the cognitive elements that are operated on in lower animals, things like beliefs and desires and percepts and so on, become objects of cognition themselves. Right? They're not just driving behavior. We can think about them. We're not just thinking about the thing out in the world. We can think about our thought of the thing in the world.
Right.
And that metacognition and introspection and imagination gives us a level of flexibility and conscious rational control over our behavior that transcends anything else in the biological world. And that, for me, justifies the use of the term free will, even though it's not an absolutist term, which would be, to be free of any constraints, any prior causes whatsoever, which to me is just incoherent. You wouldn't
Right.
be a self. You wouldn't be a self if that were true. But it means we can act for our reasons. We can inspect those reasons. We can develop those. We can choose new goals, policies, and commitments over longer timeframes that really do make us special in the living world.
But you made another point that comes to my mind as you say this, and that is it's really important that we see ourselves as a part of nature, right?
Absolutely. So there's nothing magic here. And, we don't have to reach for a kind of a mystical dualism where there's a self that's in charge that's somehow separate from the brain and immaterial kind of a thing, because then you're back in a really, an untenable position. So what I want to, say instead is that we end up in a state where the system itself is doing, when we see the neural circuits working, that's you thinking. And when
Right.
we see them doing something else, that is you making a decision. There's nothing more. You shouldn't be looking for anything more than that. That is you doing that for your reasons based on the meaning of those patterns, not just the instantaneous firing of neurons or the movement of physical particles. So I think there's a middle course between reductionism and pure kind of physicalism and mystical dualism. I think there's a naturalized middle ground which allows us to be in charge of our own actions without there being a ghost in the machine.
Right. And what did you had was it cognitive realism? Is that
Yes, cognitive. Yeah, I didn't know.
I
It's
like
funny because
that. You want to talk about that really quick?
sure. I mean, it's just a made up ism
I
name.
like it
I didn't.
though. I like it. I
I think
think
it.
it
I think it works. It finally kind of settled for me what the point is that I'm trying to make there, which is that cognition is real. right? It's not an epiphenomenon. It's not an epiphenomenon to say, oh, you have beliefs and desires and intentions, but really all the causal work is just these neurons firing. No, I reverse that. I say, no, those neurons firing have causal power in the system only by virtue of what they mean. If they meant something else, different things would happen. If you vary the details in such a way that they mean the same thing, you don't affect what happens. So the causal power in a counterfactual sense really is in the meaning of the cognitive elements. And so, yeah, I, for want of a better term, landed on cognitive realism as a descriptor of that position. And to me, it provides a naturalized way of thinking about mental causation, right? Which is, so people say, well, how can having a thought push physical stuff around? That's ridiculous. The immaterial thought can't intervene in the physics of your brain. Well, thoughts are not immaterial. They're physically instantiated in patterns of neural firing, but they're not reducible to those patterns, right? They're patterns that mean something, and the system is configured in such a way that the meaning is what drives the mechanism. So for me, yeah, those things provide a way of thinking about cognition and psychology and the relationship to neuroscience without reducing them to just neuroscience.
Right. And one of the things I also appreciated about your approach was that it doesn't require emergence, because emergence is one of those words that ends up feeling non-scientific to most people. And you make the point, I loved it. The one that made the comparison to the players on the football team. You remember that?
Yeah. Yes.
Can you reproduce that?
Sure. Yeah. Yeah. Emergence is a tricky topic. And in one sense of emergence is strangely reductive, actually.
Right.
The idea is that what happens at the higher levels emerges from the behavior of the individual components. And so if you look at a flock of birds, for example, you can see that kind of emergence, which to me is not super interesting. It looks cool when they're flying around doing a murmuration, right?
Yeah.
You get some collective patterns that do really come from individual elements. But I'm more interested in organization and functionality, right? And that does not emerge from the low level things. And so, yeah, I use this example of football players. The way that they move does not define the strategy, right? The strategy doesn't emerge from the way the players move. The strategy is imposed top down and constrains the way the players move. And that, for me, is a kind of a top-down relationship that, again, it is not magic. It's totally commonplace.
Right.
I don't understand why people have such a hard time with this idea, like it somehow violates our notions of causation. It's utterly commonplace. Organization matters, right? And that's, I think, an interesting example. And if you look at evolution through that lens, then what you can see is that evolution is driving some top-down strategies by selecting the ones that work. And it's saying this organization works because it has these functionalities that help a living system persist through time. And one of the flip sides of that is to think of where those functionalities come from. And it can feel like there's a free lunch, like they're just popping into existence when you organize things a certain way. I like to think of evolution as more exploratory than inventive. So it's exploring this space of possible organizations, some of which just have functionalities in an abstract sense. When you put together components in a certain way, they'll act like an oscillator or a filter or a coincidence detector or an amplifier. Those are just abstract systems principles that are kind of platonic, right? They just sort of mathematically hold true. And when evolution sort of happens upon organizations that have those functionalities, then it keeps them, right? If they're useful for the organism, it keeps them. But I would say it doesn't invent them. So, yeah. So in the end, I don't talk about emergence much because I find it such a confusing word that it does more harm than good in these discussions.
That's why I love that you mentioned that, because it really says, hey, we can explain this. We don't need to use a vague word like emergence.
Yeah, I think that's right. Yeah.
Right. And gosh, and then the time frames are really hard to get your head around because, I mean, I think you mentioned that the single-celled organisms were around for about 1 billion years before multicellularity.
Yeah.
I mean, so if you could even get your head around that amount of time, then you can begin to see the random changes of mutations and all as working. I mean, if you think in terms of the time we live in, it makes it really hard to think of that as a realistic way for things to work. So you really got to stretch your brain to to that
Yes.
huge amounts of time, which is really, it's very hard to do.
It is. I think you're absolutely right. We're not psychologically predisposed to be able to handle those concepts. I mean, it's almost infinity, really, from our perspective. But yeah, that's the amazing power, right, of evolution is when it's this simple algorithm. Vary, select, repeat.
I mean,
Reproduce,
even the
repeat.
time when the dinosaurs were alive was about 100 million years, which even that number is just
That's a
boggly, right?
yeah, that's a big number, a long time ago. So yeah, evolution has had plenty of time to explore, to find the designs that work. I mean, evolution basically does design work. And one of the upshots of the book, one of the central messages really, is that organisms can have causal power to act in the world by virtue of the fact that that causal potential has been packed into them by all that design work of evolution that packs causal potential into an organism, as well as the individual learning that an organism does, organisms with nervous systems at least, through their own lifetime. So all of that work, right, the payoff for paying attention
Mhm.
to how things have turned out over time, either evolutionarily or in an individual lifetime, is the causal power, the knowledge that's in the organism about the way the world works and the way it models itself in the world and what it should do. That's where that causal agency inheres. That's where that power comes from. And I like to think of it like potential energy, although it's probably not a direct parallel, but there's an analogy to be made there, at least, that organisms are causal capacitors. Right?
Right.
They build up causal power by a history of causal intervention in the world and by paying attention and basically building up a store of causal knowledge that can then be deployed in new situations.
Right. And some of that knowledge we, in a sense, have inherited because, like, if you think of vision and some of the visual illusions basically show
Mm-hmm.
that we process things with the assumption that light's coming from above, right? So we
Yep, yep.
see things to be the way, whether they look like they're up or down, or all those convex, concave, illusions are based on the fact that our brain, our visual systems have evolved to expect that the sun's above us, that we're on this planet with sun coming down.
Yeah,
So I just
yeah,
think
and
we should not
that's
underestimate the value of our evolutionary heritage. I mean, that's something I'm coming to appreciate.
absolutely, yeah. No, we're very well adapted to the regularities of the world that we evolved in and that we inhabit. The one thing that's sort of different about us is that we have this capacity for behavioral flexibility that's almost unbounded. And that really means that we can inhabit the most dynamic, changeable environments. That's why we've been able to colonize the whole planet. It's really what sets us apart from other animals, is that degree of cognitive behavioral flexibility, which is, of course, an evolutionary endowment.
Right.
I mean, that's what evolution gave us. That's why we're able to have this conversation.
So, Kevin, do you have any advice for students?
Well, let's see. I guess maybe it depends on students of what, but generally, I would say I would encourage students to read widely, read outside your discipline. For me, in my own career, I've had, I think, the most sort of insights, personal insights from an idea from some other area that I can see actually, well, you know what, maybe that gives me a different way to think about this thing in my own field. And any field can get into some kind of conceptual ruts. It has some conceptual habits, ways of thinking about things that may be completely productive, but they may also be partly or totally wrong. And sometimes getting inspiration from some other field can be really useful. So yeah, I think reading widely, just take your head up every once in a while. Of course, students, they want to get in, they want to do their projects, they want to study for the classes that they have and so on. But yeah, it's worthwhile being a little more sort of intellectually omnivorous, I think, and looking around a bit.
Yeah, and I've been hearing that from many of my guests recently, and I think it's so incredibly relevant, especially in neuroscience, which depends on so many other fields. Like here you are, a geneticist doing neuroscience, right?
Yeah. Yes.
And Seth Grant's a molecular biologist doing
Yeah. Yeah.
neuroscience. So in the early days of neuroscience, it seemed like they were all physicists.
Yes.
And guys are still coming from physics, but yeah, and I wish we had a better way for the fields to to be more interdisciplinary. Because like you said, you get these ideas over here that the philosophers have, and you got this stuff that neuroscientists have, and they don't really talk to each other. They just tend to criticize each other. The neuroscientists are really bad for saying, oh, we don't need philosophy.
Yeah, I think that's right. And, neuroscience of all subjects is so interdisciplinary because it spans so many levels, right? You've got people like Seth Grant, for example, working real protein components of synapses and so on down at the molecular level. And then you've got people doing, fMRI experiments in psychology, cognitive science kind of stuff on whole human brains and everything in between. And what we really lack, I think, is and kind of an overarching theoretical framework, or at least a conceptual framework that allows us to go from one level to the next without what I often see, this sort of temptation to go from, here's a gene associated with risk of schizophrenia, and here's how it explains why people's working memory is affected, or why they're having, psychotic hallucinations or something like that. And people wanting to make a jump from one level to like 10 levels above, as opposed to going step by step. And so that gets us into trouble. And it's a bit naive and reductive, actually, that sort of approach. And I think the only way to get around it is to have this sort of integrative systems view that can see that the system at the high level is made of these subcomponents without feeling like you're thereby reducing everything down to the lowest levels. And then you end up with this question of, well, wherever should we stop, right?
Right.
So, yeah, in a sense, I guess that sort of framework is what I try to present, is a non-reductive systems view of what brains are doing as opposed to just what's happening in them, which is often the object of study of a lot of neuroscience.
Right. Well, I enjoyed the book very much, and I'm looking forward to sharing this interview with my listeners.
Well, thanks very much, Ginger. I really appreciate it, and I appreciate the chance to talk with you.
Okay, that was a pretty intense interview. Before I go through the key ideas, I do want to share just a few closing announcements. As always, you can find complete show notes and transcripts at brainsciencepodcast.com, and you can send me feedback at brainsciencepodcast@gmail.com. You can also get show notes automatically via the free Brain Science newsletter, which is available through the website and by texting Brain Science, all one word, to 55444. And you will get a free gift, which is called 5 Things You Need to Know About Your Brain. I mentioned in the intro that the show is supported by listeners like you. If you'd like to learn more, go to brainsciencepodcast.com/premium. If you are a My Lips and Premium subscriber, I want to remind you that one easy way to access your premium content is through the free Brain Science Podcast mobile app. It's also a great way to access new episodes if you're a person who likes to listen to podcasts in an app. But you can always get Brain Science wherever you listen to audio. I am now in New Zealand, and as you might be able to tell, I'm still trying to come to grips with the New Zealand germs. I've really enjoyed hearing from some of you who live here in New Zealand and also over in Australia. I would really like to organize some listener meetups, probably starting out in Auckland. So if you're interested, please email me at brainsciencepodcast@gmail.com. Finally, I want to mention that there is not going to be an episode of Brain Science in November 2023. That's going to give me extra time to work on the year-end review episode, which is going to come out probably on December 15th, because that corresponds to the 17th anniversary of Brain Science. I want to thank those of you who've been here for the entire 17 years, and for every one of you who listens, even if you're just brand new or you've come and go. Okay, so let's talk about this episode. Kevin Mitchell's new book is Free Agents: How Evolution Gave Us Free Will. I highly recommend this to listeners old and new. One of the implications of the biological nature of consciousness is the possibility that we don't actually have free will. that is, the ability to make real choices. This is the position taken by many prominent neuroscientists. But Kevin Mitchell argues that making choices is actually a key feature of our evolutionary heritage. Today, we talked about some of the key ideas from his new book, Free Agents: How Evolution Gave Us Free Will. But I want to start this review by reminding you that Mitchell's background is in developmental neuroscience. And in his first book, Innate, he argued that the brain is not a blank slate. Genetics and development give us strong predispositions, but even the brains of identical twins are unique because they follow different developmental pathways. I encourage you to go back and listen to that episode. It's episode 159. I mention Mitchell's background because one might expect that he would accept the mainstream arguments against free will. But instead, he observed that there is a tendency to conflate the question of free will with moral issues. He decided to overcome this problem by considering the evolution of agency, which is the ability of any living thing to make choices. Now, I'm not going to try to rehash the details of our interview in this review. Instead, I'm going to try to focus on just a few key ideas. First, by arguing that agency is a result of the evolution of life, Mitchell points out that the boundary between life and inanimate matter really is the key event. Of course, many people see living things as just complex automatons that lack real choice, but Mitchell argues convincingly that even simple organisms make simple choices. Now, a choice requires at least two key elements. The action has to be more than a reflex, which means that the same stimulus cannot always lead to the same outcome. Same stimulus can lead to multiple outcomes. And the second piece is that it has to depend on past events. I really encourage you to read Mitchell's new book to get the details of this argument. But many current arguments against free will are also based on the assumption that the physical universe is deterministic, which is to say that in the end, everything comes down to the action of subatomic particles, which are predetermined by the past. What does the physics really say? Here's things get a little strange because we've had quantum mechanics for over 100 years. It allows incredibly precise predictions, but it's actually based on the realization that the world is not deterministic. And this really matters because if the physical world is deterministic, then there will be no room for agency or choice. We would be back to the predestination of Calvinism. I highly recommend the book Helgoland, Making Sense of the Quantum Revolution by theoretical physicist Carlo Rovelli. He explains his relational interpretation of quantum mechanics, as well as reflects on what quantum mechanics does and does not mean for consciousness. The bottom line is that contrary to many well-known neuroscientists and philosophers, Kevin Mitchell argues that we do have the ability to make real choices, which is the kind of free will that matters. The key elements of his argument are that the physical universe is not deterministic and that agency evolved with life. Now, we touched on many details during our conversation, but we didn't really address the experimental literature that purports to show that agency is an illusion. You will find these experiments discussed in the book, and there is a growing literature challenging these conclusions. I will put links to these additional references into the show notes. Before I close, I did want to touch on why humans have brought agency to an unprecedented level. We talked about metacognition in episode 185 with Peter Fleming. Mitchell points out that humans are capable of metacognition, thinking about thinking. This allows us to take agency to a new level. We can analyze and judge our past choices. We can anticipate the consequences of our future actions. Does this give us a new level of responsibility? I actually recorded this interview before I left the United States with the intention of releasing it in October 2023 to coincide with the release of Kevin Mitchell's new book, Free Agents: How Evolution Gave Us Free Will. I highly recommend you read this book yourself. Mitchell mentioned after we finished recording that he will be doing some debates with Robert Sapolsky, whose new book, Determined: A Science of Life Without Free Will, argues for the opposite position. You'll find links to both books, along with episode transcripts, at brainsciencepodcast.com. And, of course, you can email your feedback at brainsciencepodcast@gmail.com. Before I close, I do need to remind you that there's not going to be an episode of Brain Science next month, November 2023. I intend to release the 17th annual review episode on December 15th to coincide with the 17th anniversary of episode 1, which was released on December 15th, 2006. Many of you have been with me from the beginning, so I want to thank you for your support. Thanks again for listening. Until next time, please check out my other podcasts, Grain, Rainbows, and Books and Ideas. Brain Science is copyrighted to Virginia Campbell, MD. You may copy this episode to share it with others, but for any other uses or derivatives, please contact me at brainsciencepodcast@gmail.com. The theme music for Brain Science is Mind Fire, written and performed by Tony Catraccia. You can find his work at syncopationnow.com.